guys, this is the FRC coding class day 6, and today we're going to start the introduction, or we're going to start FRC coding specifically. We were working on Java, kind of as just that would work for anything. This is going to be specifically robotics. Okay, so the schedule is today we'll introduce some basics, and then we'll talk about sensors, user input, and state machines. I'm not sure how long it will be, probably a little longer than the others. The next class will be on motor control with PID and advanced motion control. The class after that will be writing subsystems, and the fourth will be code structure and flow, and then maybe using GitHub. Um, so after this class, it should be 3 classes. It might end up being 4, just depends on how long some of these things take. Okay, so a basic introduction is that each robot has one project in Eclipse. So if you notice, I don't know if you guys have been making multiple projects, but in the little navigator on the left, there's basically folders. Those are called projects, and so each robot will have its own. And since we have multiple people working on the project, we use a tool called GitHub, which will basically it'll sync the whole project across everyone's computers. You can view it on the web, and the nice thing about it is you can go back. It'll show like version history, and I can see all the history of who made what changes, and if I want to revert something, or if I want to go back and look at stuff. It's used in the industry. Basically, everyone who does programming uses GitHub. Like GitHub's what you use. I would recommend going onto GitHub.com and making an account, and then, well, I guess you don't need to do that yet, but hopefully by week 4 we should have everyone in the GitHub. So we write code on the robot for the motors. We actually program the main computer board on the robot. This little gray box I'll talk about later, and we basically take the code on our laptop and run a command in the command line to basically send that code over to the RoboRio, which is the main processing board of the robot, and then that will send signals to these little devices called motor controllers, which then output power, specific power to the motors. So we'll end up controlling the motor controller. We don't actually directly control the motor. The motor controllers do that. The nice thing about motors is they can have variable rotation and variable speed. And pneumatic cylinders is another thing we use. Basically, these are pistons that give you linear motion really quickly back and forth. I'm not going to go too much into the mechanical stuff or electrical. I'll try to stay away from that, but it's nice to have a decent background. Basically, they use air to move stuff back and forth, and we have a little solenoid which will flip the switch between where the air goes to move it back and forth. Another thing we program is sensors. So all of these I've been talking about, you give output to, sensors give us input that we can use to figure out how to move stuff around. Most motors will have some sort of reduction in a gearbox. This isn't super necessary, but in your code, you might hear me talking about gear ratios and the final output speed. Basically, the speed at which the motor spins is usually different at the speed at which the actual mechanism will move. We separate the robot code into different sections that we call subsystems. I think I've talked about them a bit briefly, or maybe other people on the team have. Each subsystem has their own file or class in the robot code. There's also a ton of other classes for other things, but Tsunami, our 2020 robot, had 8 subsystems: the drivetrain, climber, flywheel, hood, hopper, intake and paneler, and turret. It seems like a lot. We sometimes differentiate them a little bit differently. Basically, each subsystem will have as many sensors as it has, and usually one motor or 2 motors. There is some exceptions though, but just how the code runs. Okay, so I'm just gonna briefly talk about some of those because I will be using our 2020 robot as a reference. So the drivetrain is these 6 wheels you see here with these 4 motors down here and a little gearbox there, and so this allows us to move around the field. You spin this side of wheels forward and this side of wheels forward to go forward, this side backwards, this side forward to turn this way, and then I guess you can assume the other ones. On the front, we have this little thing that flaps out, which is called an intake. Basically some wheels that spin and suck up 7-inch dodgeballs or power cells. This is, I'm not going to cover I'll go do it. The paneler is a little device that flips up with this pneumatic cylinder here. So this thing also here is a pneumatic cylinder. If you're curious, it moves this back and forth. This is one here also, a smaller one. So this whole mechanism flips up, and there's a wheel on top that spins a giant another wheel in front. Sorry if it doesn't make too much sense. I'll try. If you have questions, just put them in the Discord, and I'll try to answer them. This is our shooter. What this does is it gets fed 7-inch dodgeballs. There's a giant sprocket around here which has a chain. I don't know if you guys know what like a bike chain is, basically that. And you power this with a motor down here, and you can spin this whole shooter mechanism, and that's called the turret. Then you have the adjustable hood, which is this red and black piece here. This will move out like this, and this adjusts the shot angle, if that makes sense. And then here's the flywheel. These two motors spin the flywheel up to 9,000 RPM. So basically, a ball gets fed in here. The turret adjusts, this direction. The pitch or yaw. The adjustable hood adjusts the pitch of the shot, and then this adjusts how powerful the shot is, and actually launches it, obviously. And we have a camera on front. This isn't super useful, but this will be used for automatic aiming. Okay, first I want to talk about sensors. What is a sensor? So basically, you probably have a rough idea of what a sensor is. It's basically something that can detect or measure a physical property and translate that into electrical signals. So why we use them to detect game objects, the position of mechanisms, the angle of the robot, etc. We use a ton of sensors across the robot, and we use this data to more effectively control our robot and use to automate the robot, so that the goal of the code is mostly to translate a driver using an Xbox controller, translate their inputs into the robot movement, but the other goal is to reduce the amount of things that the driver controlling the robot has to do. So a lot of the stuff especially on our last year's robot, most of it is automated. When you press a button or you move something, the robot is usually handling a ton of other things, and it's just kind of simplifying it for the driver. I kind of have to cover some of the mechanical and electrical for you guys to understand how the code works. And so I think this it's kind of a gray area between what's exactly programming and electrical, but let me cover this in case you don't know. So voltage is a change in electrical potential. I like to think about it, if you change the voltage you're giving a motor, it changes how fast it's spinning. So our motors operate off 12 volts. If I go 12 volts, it'll go full speed. If I give 0 volts, it'll be stopped. And amps is how much force is getting applied against the motor. So you send it this is not really how it works, but you choose how much voltage you send it, and then it kind of gives back an amp. So that's not really how it works, but it's kind of simple to think about it that way. If I were to hold my hand on the shaft of the motor while it's spinning, the amps would spike up. Whereas if it's free spinning, the amps are pretty low. Something for sensors is super useful to know. Well, actually, first, the voltage of sensors can be 0 to 5, usually, or 0 to 12. The whole robot is usually 0 to 12. Analog means variable voltage. So there can be anywhere. It could be 2.5 volts. It could be 6 volts. Anywhere from 0 to the maximum. Anywhere in there. And depending on the sensor, it could be very accurate or not so much. And so that will be less common, I would say. Digital sensors are a lot more common on a robot, I would say, or at least the custom sensors we implement. A binary voltage basically means, like a Boolean true false. Basically, that's what it means. It could either be triggered or not triggered, 0 volts or 5 volts, or if it's a 12-volt sensor, 0 volts or 12 volts. So I'm not gonna try. I'm just gonna briefly cover this, but I'm gonna keep this as a good reference for you guys. This is the main processing board I was talking about, the little gray box, and this thing's, maybe 4 or 5 inches by like a square. And there's a couple ports we'll use on here. This is basically you plug in a sensor into some of these ports, and they will allow your code to access them. There's other ways we can read sensors. Sometimes we'll plug a sensor into the motor controller. Sometimes the sensor will be built into the motor controller or motor, or sometimes they'll hook into different ways. Relatively, you don't need to know that too much, but it is nice to know kind of where it is, roughly. So when you plug a sensor into the RoboRio directly, you can access it in code by making an object called digital input. So you can't actually do this now. I'll have to integrate you guys into the whole FRC library suite type thing, so you can actually write FRC code in Eclipse. Right now this will not work if you try to write it. There's an object called digital input, and you make one of these. You can call it whatever you want, obviously, and then you input a port. So on here, there's the digital input output ports, and so see the numbers here. You can kind of see that. Oh, it's plugged into port 0. Okay, now I put it port 0 here. Same for the analog right here. The analog sensor, you can either get the voltage, you can get the voltage averaged over a certain amount of time. You can get the value, which I think is in percentage. There's a ton of other things. As you can tell, an analog sensor is just, there's not much like at first jeez, at first it might seem like they're pretty similar, but this one has a lot more complexity to it, and usually you do not need that complexity. Now I talked about having a sensor hooked into the motor controller or into the motor. We have some motors that have motor controllers on them. I'm gonna try to stop talking about electrical stuff, but anyway, there's an object for the motor controller called Talon SRX, and there's an ID, which I'm not going to cover how you get that, but you'll usually see this in the code for you already, and there's a method down here for it. Again, you don't have to memorize this stuff. I'm just going to give you a rough idea of kind of how you would implement it. Now I'm going to go back to electrical. I guess this is an electrical presentation because usually the programming team chooses what sensors they have, and then the electrical, or sometimes does some stuff, and then the electrical team will put them on the robot. But there is a lot of collaboration between that, and so usually both sides need to have a rough understanding. So these are the most common ones we use. You will definitely encounter all of these sensors at some point. Maybe not this one as much, but yeah. This first sensor detects magnetism, and so it sounds more complicated than it is. Basically, there's things called limit switches, which we don't use because of many reasons, which is like a little button basically. If it's pressed, it's true. If it's not, it's false. A magnetic sensor like this works in a similar way. So you have a magnet on your joint, and this is fixed somewhere. And as they get close, as they touch, or as they get close, the sensor detects that. The nice thing about this is they don't have to hit each other. If the mechanism were to have to hit a limit switch, physically move like a lever, then obviously you can see how that could get damaged. This way there's nothing physically contacting each other, but getting really close. This is a gyroscope. You've probably heard of a gyroscope before. This can measure all angles, yaw, pitch, roll, in 3-dimension, the 3-dimension, like that. And it's also an accelerometer in 3 dimensions, X, Y, Z. We will not use the accelerometer at all. It is very inaccurate, but the gyroscope is very accurate. And this sensor we will use to control, like figure out where the drivetrain is on the field. This is an encoder. This is also a way we can figure out where the robot is on the field, but we also use an encoder to figure out where any of our mechanisms are. This is probably the most important sensor that we use. It's on everything. What it does is, this specifically is a magnetic encoder. We really like our magnets. This magnet would be like kind of vertical like this relative to the sensor, and as it spins, this little sensor picks up how many revolutions it has spun, and the goal is that you can kind of track how much it spun and then calculate like how fast the actual mechanism, like account for like gear ratios and stuff, and then you get a final output speed, and you always will know where it is. And so usually you'll see in combination of these two things. Let me flip back to the robot for a second to explain this. The motor here has a built-in encoder, and so if you think we calculate all the gear ratios to here, we can figure out how much the turret has turned down to like 0.01 degrees or 0.1 degrees probably, and that's super useful. But the thing is if I turn off the robot and move the turret and turn it back on, the turret still thinks it's here. So we need some way of figuring out where the turret is, and so now we use that magnetic sensor to detect, like limit switch sensor basically. So there's a magnet right here, and there's that little magnetic sensor here, and so whenever we turn on the robot will turn until the magnet gets in range of that sensor, and then it's like, okay, I'm at negative 135 degrees or whatever, and then it'll turn back straight, and now the encoder will always know where it is, basically. This is the same thing here, but built into something. You might see this there, the same thing. This sensor is an example of a digital sensor, same as this one. This one, instead of detecting magnets like here, this one detects breakage in a light beam. And so basically it shoots out, from what I understand, it shoots out a sensor or laser, 50 millimeters, and reflects it back to here. And if anything obstructs that 50 millimeter light beam, the sensor will trip, basically. And this sensor is very similar. This was actually kind of a more expensive version of what you see in your garage, called a beam break sensor, which works very similar to this, except this one shines out a laser into a retroreflective panel, mirror basically, which reflects it straight back, and that will detect any breakage in that beam. This one is nice because you don't need a mirror, but it is less effective, or not effective, consistent basically, even although we still use them a lot. These ones, if you really need that much consistency, you could use them, but relative for FRC, it doesn't matter too much. Okay, driver input, or user input. So, as I mentioned before, there's a person controlling the robot with an Xbox controller, except sometimes the robot controls itself, but we don't really need to cover that too much. So let's just assume it's always user control. So it starts off. So as I mentioned before, a lot of the sensors are plugged into the RoboRio, or kind of indirectly plugged into the RoboRio. If the controller is completely wireless from the RoboRio, how does it get to it? And so that's what this kind of diagram explains. So a controller is plugged in from USB into the driver station, which is a app running on a laptop, which then connects over Wi-Fi to a radio, which is a little white box if you see it, which is then uses an Ethernet cable into the RoboRio. Bit complicated process, but overall, something to note is that there is a delay. I would say probably about 20 milliseconds or less, probably a little less, but that is something to note. So, how your code gets the data, or how your code reads what the RoboRio is receiving. You make a object called Xbox controller, which is built in. Again, you can't do this right now. Name it whatever you want, and then port 0. If I had like 3 controllers plugged in, they would be listed in the order they were plugged in. And then there's a bunch of methods like get A button pressed, and when you press the A button, it'll trigger, or get Y axis, which will return you a analog value of what the Y axis is. This is super useful. in our actual robot code, we use a different class that we made ourselves that's a little more convenient. Um, but for now, this is something I'd use. And also for prototyping, we use this all the time. When we're prototyping, we kind of throw together some code, and it's usually super messy, but we just need something that works while we're kind of testing it out. And then later on, we'll go back and make a good code structure. So, just some tips on using controller input. You probably don't need to know this, especially Will, but this is just a good reference. The goal, again, is to reduce the number of buttons for a cycle, which is like going back and forth and like, picking up balls, shooting them. That's one cycle. Reduce the number of buttons. So our goal is to have like 1 to 2 buttons. For us, you press the X button, which will do a bunch of things. It folds down the intake, it spins up the wheels in the intake, and then it does a million other things. And then as soon as you finish picking up all the balls, it automatically comes back up and everything. And then there's just one more button to shoot. 2 buttons for the whole thing, and the robot does a million more things. But the goal is that, again, the driver's concentrating on the game and not pressing all these buttons. Allow the driver to press buttons ahead of time. This wasn't especially apparent in this year, but in other years, if you had to change a bunch, if you had to like, in 2019 there was a lot of customization. I know you guys don't know the robots, so it might not make a lot of sense, but basically we had a mechanism that moved where you're going to place it from 3 different locations, and instead of having to get there and then in the slick of time figure out like what side and what height to go to, instead the driver, like, while they're not really focusing on anything else, while they're driving there, they'd press those buttons, and then when they get there, they just press go, and then it already knows what height and area to go to. The other thing is, don't have locking states. I'll come back to this when we talk about state machines. Basically, yeah, I'll come back to this one. Put the most used buttons in easily accessible areas, and put the least used buttons in the least accessible areas. So, I don't know if you guys know what an Xbox controller looks like. Here's a diagram, for example. The most common things we did, the driver puts their left thumb here and their right hand thumb here, and so obviously you can tell these buttons are very easy to access, and that's intentional. Why we put the most common things on here. So intake that I talked about and shoot button, these are the most commonly pressed, and so they're the most easily accessible. Whereas something like over here, this is harder to get to, but it's fine because we press this once in the entire game, if that makes sense. This is our controller layout from last year, and you can kind of look at it for reference. I'm not going to go into detail too much about it. Yep, that was it. State machines. Basically, state machines are a model that have a bunch of potential states, but is in one of them at a time, and you can transfer between the states in a set order based on an input. Basically, that's just mumble jumble for saying there's a bunch. I don't actually. That's probably a good way of describing it. Let me give you an example so you can kind of have an idea. Let's think of traffic lights. There's 3 possible states, right? So has 3 potential states: red, yellow, or green, and then it's in one state at a time. It can't be red and yellow at the same time, and it changes based on the time or number of cars waiting. That's the input right there. But then there's also a set order, right? You can't go from red to green. You have to go in red, yellow, green, or green and then green to red. What am I saying? I just mixed that up, but you know what I mean. Here, exactly. And then these are kind of the states between them. The benefits for robotics. Usually, your robot will always have a state machine, even if it's unintentional. Like, you might not have a written out state machine, but there is a state machine there. But clearly defining the state machine is super useful and really easy to understand for the driver to understand what the robot thinks should be going on and what is going on, and for a lot of other things. So they help sync all the subsystems together. you don't want the intake to be doing one thing and the shooter to be doing something else. You want them all to be kind of working together. It ensures there's no conflicting instructions. So let's, for example, say that, oh, actually, that was a perfect example. Let's say the intake is trying to pick something up while the shooter's trying to shoot something at the same time. I mean, that would, for example, wouldn't be terrible, but that's just something we want to avoid. A logical progression of actions. So, for example, the robot can lift itself up onto a bar, and so we have a state called climbing. Basically, it is lifting itself, but you never want to be able to go into climbing without going through the state uh, deploying climber. And so you should never be able to go from shooting a ball into climbing. That makes no sense. That just would break the robot. And so that gives you a logical progression of actions and kind of a forced state machine. Here's an example. It's kind of a bad diagram, but basically, this is a simplified version where they can all switch between each other, but they all go through idle. The idle state is just you can drive around, but nothing's really happening. I mean, some stuff might be happening, but relatively nothing. So you can go to intaking, you go to aiming, shooting, climbing. Again, there is climber, like deploying climber in front of this, and so you can only swap between those. But let me go back really quick before I forget. I mentioned don't have locking states. This was a big issue we had in 2018, where let's say I'm in climbing, because actually climber deployed climbing, I wouldn't be able to exit that state. Like I could, like there's no way I like let's say something happens, I just want to quit and I want to go back to idle. The driver, there's a button on the controller, right here called idle. No matter what's happening, if they press the idle button, it goes to idle no matter what. It, like no, even if it breaks the robot, it goes to idle. And this is because you could have a thing where you accidentally start climbing, or I don't know what happens. You always need to be able to exit your state because there's always some code glitches or something. You just need to be able to exit the idle state. Okay, that was it for the class. I'm not sure how long this video was. Tell me if I should do less classes that are a little bit longer, or the other way around. I didn't put practice problems because, again, you can't really do this stuff right now. We need to, I'm going to try to post some material maybe for next class or the class after, or not material, like a Google Doc explaining how to install some of the stuff. Hopefully it'll work for everyone's computer, but the goal is that we should be able to at least write some basic FRC code, and in worst case, we'll just at least have you look at it in detail. So the next class, again, we'll be covering motor control, control theory. It's probably a lot more interesting than this class, I swear. I hope this interests you guys at least a little bit. Tell me how I could make it more interesting if it's not. Yeah, that's it.